Hey everyone, it's Mrs. Shannon. So hopefully if you've made it this far, you've been able to go back onto Canvas and navigate the page and find the modules, and you are in the screencast for the biochemistry Prezi. There are a couple of these Prezis. It's broken down a little bit. The first one is more of a chemistry review. And so if you've had chemistry, even if it was a basic chemistry, a lot of this will be familiar to you. If you don't remember it exactly, hopefully the vocabulary at least will be recognizable, and through the course of it, you'll get enough out of it that you need. If you have not had chemistry, you will want to pay a little bit more attention. Same thing with the reading. If you are comfortable with the concepts being discussed, you could probably skim chapter 2 in the textbook, but if you don't feel like your foundation is very strong, you may want to go in and read a couple of sections, especially the sections on water and the different properties of water and the chemistry behind water. So we're going to split this up into atoms and bonds, water, and carbon. And let me go full screen for this. Okay, and so we're going to start over here with atoms and bonds. And for this, the idea is what matter is and where it comes from. How do the atoms interact, and how do the interactions of atoms lead to the emergence of the raw materials necessary for life? Remember, in reductionism, what we're doing is we're thinking about how the little parts that come together to build something have different properties than what is actually made. And so when you're looking at the cell and you're looking at the cellular membrane, for instance, the atoms that came together to form that cellular membrane may have different properties than the actual membrane itself. And so we're going to talk at the atomic level. For our purposes, that's the smallest that we're going to go. We'll talk about the electrons of it a little bit, but we don't go into subatomic particles. We don't go into quarks and neutrons and things like that. So you physics people, yay for you. But the atom is pretty much the smallest that we're going to go. So now that we have all these atoms, just what are we supposed to do with them? Well, we think about our chemistry. And so again, in biology, the atom's the smallest fundamental unit that we'll talk about. There's approximately 120. I know there was 100, and I'm not sure what the number is up to right now. Mrs. Fellows would probably know, like maybe 126 for the number of elements on the periodic table. In biology, we don't focus on very many of them. 4 major ones, C, H, O, and N, are the primary ones: carbon, hydrogen, oxygen, and nitrogen. Phosphorus and sulfur are 2 other ones that we'll talk about. And oftentimes, SNOPs or CHOMPs is the acronym or the word that you may remember from biology class as in the major elements of the living systems. We talk about a few others: zinc, iron, magnesium, calcium, potassium, but we'll get to that later on. Okay, and actually you can see oxygen's 65% of the human body. 96.3 are those first 4 elements that are listed in the table. Besides the actual matter itself, we're interested in the energy. The energy interacts with atoms in different ways. It either holds the electrons to the nucleus. When atoms absorb energy, energy is moved to higher energy levels. And then when it comes back down, that's when energy is released. So the energy that's needed to perform functions, it requires that movement of the electrons to higher orbitals and then back down. And so you can think of it almost like the bouncing ball going up the stairs and back down the stairs. Bonding is accomplished by electrons interacting between atoms. We're talking about the valence electrons. So remember the octet rule, and think about how many electrons are on the outside. There's 2 major bonds: ionic and covalent. Ionic is when we transfer electrons, not many possible combinations. Salts are going to be our major one. KCl, NaCl. Those are our major ionic compounds that we'll encounter. Most of the time when we're looking in biology, we're looking at covalent bonds. Covalent bonds require a sharing of electrons. Functionally, there's an infinite combination, but all the important biological molecules that we focus on, those 4 groups, for instance, biomolecules, nucleic acids, proteins, carbohydrates, and lipids, they involve covalently bonded atoms. Okay, so here's an example, the sodium, chlorine coming together. Again, chlorine's a poisonous gas. Sodium, I don't know if you ever watched the videos where they dropped just a little bit into water and it made this huge loud kaboom. This is a great example of an emergence property. Two completely different characteristics, but when you combine it together, we have table salt, something that our body needs, and that's harmless. That's not going to explode or kill us. Well, not immediately, at least. When it comes together, it has an emergent property. Okay. Not all bonds are created equal, too. So we have ionic covalent, but even when we're looking at covalent bonds, we got to realize that sometimes there's an unequal distribution, and that's usually because of the electrons. Polarity, polar and nonpolar molecules is a great example of this. The unequal sharing of electrons in a covalent bond leads to unequal distribution. And so for chemistry and what you need to know here, being able to recognize electronegativity on the periodic table is very helpful, because if you remember those on the top right, they're very electronegative. They really want the electrons. And so they are going to be pulling that direction. If you're on the right, on the left side of the periodic table, you're not very electronegative. And so yours are going to kind of shift the other direction. So even if you're covalently bonded, you're still going to have this kind of shift in one direction or another. Polar molecules are attracted to other polar molecules. So here, okay, due to the shape here, we have our oxygen, which is going to have a negative dipole on this side. It's going to be more positive on this side, thank you to our hydrogen. And so when it forms a bond with another molecule, oftentimes you'll have another positive hydrogen interacting with this oxygen. Okay. Here you have the negative nitrogen instead of an oxygen interacting. So when you see dots like this, this is a hydrogen bond. It's technically not a bond, it's an attractive force, but it's still a very strong attractive force between them. And it still carries the term bond, even though it's not a technical bond. Hydrogen bonds, though, consider them strong. Not as strong as a covalent bond or an ionic bond, but it's a very strong force. Bonds determine the shape. Again, shape is very, very important in biology. Structure and function are always related. And there's a whole section in the chapter on isomers and enantiomers. Don't worry about that section, except to know that even if it's an isomer, it has the same composition, a different structure, they are not going to behave the same. Okay, so if you have enantiomers, if you have I'm trying to remember my chemistry, cis isomer and a trans isomer, they're going to behave completely differently. They're going to fit differently in the body. And so especially if you're looking at pharmaceuticals, pharmacology, the way that drugs interact with body systems and other drugs, only one isomer may be able to work. And if you try to use a different form of that molecule, a different isomer, then it will not have the same interaction. It's all because of that shape and function. And any reaction, another thing to remember from chemistry, in any reaction, mass, energy, and charge are conserved. They are just shifted, transferred, etc. Again, when we take two small particles, put them together, the larger emerging particle or substance will have different properties, and this is shown with different compounds. The properties of a compound are different from the elements that make them, and this is the exact same that I told you before. We have sodium, explosive metal, toxic gas, and they make delicious table salt. Okay, increased levels of complexity in a system can demonstrate new properties that the parts that make them up don't show them. And in fact, like if you go into biotechnology and later on in engineering and design, you spend a lot of time looking at these emerging properties. We'll talk a little bit about radioactivity here and there, especially when we're looking at genetics and molecular biology, tagging different elements to trace reactions in the body. Atoms with unstable nuclei are radioactive, and so they emit high energy particles, and it's easier to identify them. And so they're oftentimes used in biotech fields. So any questions about the matter? Okay. Make sure in this section that you can identify different elements and explain how they are different from each other. Explain the process of ionic and covalent bonding, why they occur. So ionic give and take, covalent sharing. The idea of emergent properties, about compounds having different properties, different attributes than the elements that make them up. Polar and nonpolar bonds. We will spend some time on it now, as well as when we look at transportation across the cellular membrane. We'll talk more about polar and nonpolar. That's probably an area that you want to be very comfortable with. We'll talk about hydrophobic, hydrophilic interactions, polar, nonpolar interactions. So this is the area of the chemistry chapter that you want to really know. For the relationship between bonding, shape, and function, again, understand that even though it's the same formula, different isomers will behave differently. They may not work, they may not activate the same properties as a different isomer of it. And provide examples of uses of radioactive isotopes in biology. Just think tagging, biotech, molecular genetics, and we'll spend some time second semester talking about that. So I'm going to stop here at part 1. I'll do a different screencast for the next section, okay? Again, let me know if you have questions. Send them to me or bring them into class.